recording. Okay, cool. All right, here we go. What is the date today? There we go. It's the 7th. Okay. Hello, everyone, and welcome to the Weekly Space Hangout for Friday, October 7th, 2016. I'm Fraser, Cain, publisher of Universe Today. This week, we're going to have a bunch of cool news about the new test from Blue Origin. We're going to be talking about the Sputnik Anniversary. We're going to be talking about Maven's Anniversary. We're going to be talking about giant plasma balls ejected from stars. What happened with Hurricane Matthew and ultra strange, ultra cool brown dwarfs. So cool. So strange. Joining me this week, we've got our regular cast of characters, and I'm just going to put them all up, all on the screen at the same time. No, wait. Yes, I am. All up on the screen at the same time. And let's see. So it's going to be like the old Brady Bunch view. So there's everybody. So we got Kimberly Cartier. Kimberly.
Hi, Fraser. Hey, viewers.
We've got Paul Matt Sutter. Paul.
How's it going?
We've got Sandy Springman. Hey, Sandy.
Howdy.
And we've got, as you can see, a special guest, which is Paul Geithner from NASA's James Webb Space Telescope. Hey, Paul. Welcome to the Weekly Space Hangout.
Hey. Nice to be here.
Let's see if this works. No, that didn't work. All right. And we should be able to do this. Yay, technology. Okay, great. So as always, this is sort of the first half of the show where we're going to have a chat with our special guest and talk all about the James Webb Space Telescope. And of course, if you've got some questions about the Space Telescope, please put them in the chat and we will pass along some information. And then we'll switch on to the news side of things. So Paul, once again, welcome to the Weekly Space Hangout. It is a total honor to have you here, and it's sort of good timing as we're nearing the launch of the James Webb Space Telescope.
Yeah, indeed. It's great to be here. Thank you.
All right, so why don't you give people sort of your intro and background of who you are and what you do?
Sure. Well, I'm the Deputy Project Manager Technical for the James Webb Space Telescope project. And I'm at NASA's Goddard Space Flight Center in Greenbelt, Maryland. And we manage the whole project from here. And I've been on this project since right after the second servicing mission to Hubble. I worked on the first two Hubble servicing missions and then became the first mission systems engineer for this project back in 1997. And I've been working on it for most of those years since. It's been a long time. It's really exciting right now because we're getting quite close to launch in 2018.
Now, I have been reporting on space news for 17 years now, and it feels like a good part of that. We've been talking about the James Webb Space Telescope. I think I could go back pretty far into the archive and find information about James Webb. So where are we on the timeline of the construction of James Webb, and how much longer do we have to wait?
Okay, well, yeah, we're pretty far along. I mean, the first 10 years or so was PowerPoint and inventing the inventions necessary to make the mission feasible. And then a lot of design work, and it's in the last handful of years we've been actually building everything, and now we're in the final assembly and testing phase. So right now, well, there's four main elements of the whole space observatory. There's a spacecraft bus that's got all the comm and control systems in it. There's a tennis court-sized 5-layer umbrella, the sun shield. There's the instrument package. There's 4 cameras and spectrometers that are taking all the data, get all the light from the telescope optics, and then there's the telescope itself. And those 4 things are almost all done. In fact, the telescope and the instrument package are done, and now they've been assembled into one piece. And that's at Goddard right now. In fact, you can see it on our webcam. And we're getting ready to, we're pretty much done assembling it. A few more odds and ends to stick on there. And then we start testing it, and then we'll eventually send it to California where it'll meet up with the spacecraft bus and the sun shield and get put together into one observatory, and then we ship it to South America for its launch.
Yeah, we've got a great time-lapse view of the construction of the telescope and sort of people moving around, and you can kind of see the size of the telescope and that great big mirror. So can you give people sort of a sense of the scale of what we're dealing with here? Like how, we all love Hubble.
Yeah.
and we'll get into sort of some of the downsides of James Webb, but I mean, this is Super Hubble. How is this going to really kind of fulfill our astronomy Christmas?
Sure. So, I mean, James Webb is the successor, the scientific successor to Hubble, but it's a different kind of beast than Hubble. Well, Hubble's like the size of a Greyhound bus. James Webb is like the size of a 737, and it kind of picks up where Hubble leaves off scientifically. So Hubble can't quite see the epoch of the very first luminous objects in the universe, the very first stars, the very first galaxies. And that's one of the main reasons we're building Webb, is to see the very first light that shined in the universe. Sometime between
Hubble's deepest
380,000 years after the Big Bang, when things cooled off enough and the universe with ordinary matter, part of the universe was plasma, and it condensed into neutral hydrogen and helium. And somewhere between that time frame and maybe a couple 100 million years thereafter, that's when the universe just popped and came alive, ordinary matter-wise, and turned into stars and galaxies and massive black holes and the whole 9 yards. And but nobody's actually seen that epoch in space-time. So James Webb is designed to actually see those very first luminous objects from that time. I mean, we have satellites that have seen earlier than that. I mean, the cool pictures from WMAP and COBE, the picture from that 380,000 years, that's as far back as you can go using light to probe the universe. I mean, we've seen that, and that light's in microwave frequency, but we're actually looking for the first visible and ultraviolet light emitted by stars, which appears to us today as infrared light.
And right now, I know that like when we see those pictures from the Hubble Space Telescope, and they say like, the most distant galaxy ever observed, a lot of that imagery is done using gravitational lensing, where you've got some foreground galaxy that's acting like a natural telescope to reveal the more distant universe. And it's just, you get those alignments, and then you get access to these more distant objects. But James Webb is just going to brute force this stuff directly, right? It's just going to be able to see right out to the edge of kind of what we can see wherever we want to look. Yes,
that's true. I mean, we have 7 times the collecting area in our mirror that Hubble has. So, you think of the main optic of a telescope, it's like a light bucket that's collecting photons. So we have 7 times more area. When you add up the area, the diameter, and the sensitivity of our detectors, and all that, it adds up to about 100 times more power than Hubble has. So, in fact, our sensitivity is so good that we could see a match struck on the moon within a second of integration time. And it's nano-Jansky sensitivity. And in fact, our background, when you think about thermal background and noise from electronics and such, our sensitivity is limited by infrared light scattered and re-emitted by dust in the inner solar system. We're that sensitive. So it's pretty crazy.
I mean, we see objects that are, right now, via as I method, using gravitational lensing, we're seeing stuff that's maybe 500 million years after the Big Bang. Really, how far are we going to be looking back?
A little bit farther back than that. So maybe half again to the Big Bang. So a couple 100 million years after the Big Bang. I mean, it sounds like a small difference, but in terms of redshift and how much the universe has expanded in that time, it's actually a big deal. I did want to say something about why we're building an infrared telescope.
Yeah, well, I was going to talk about the downside, because everyone is so concerned with or loves Hubble, and although this is going to be a really powerful telescope that's going to overlap, there's some downsides to it, right?
Yeah, I mean, well, Hubble's been up there since 1990, and we've stopped servicing it a few years ago. We don't have the shuttle anymore, but it's still working. Hopefully it'll keep working for years to come. But it just doesn't have the capability to see what the very first luminous objects. And that's because if you want to see visible light emitted by the very first stars to form in the universe today, you need an infrared telescope now to see it. And that's because ultraviolet and visible light emitted by those first stars has been stretched so that they're longer wavelengths of light. Now they're infrared light by the time it reaches us today, just because the cosmos has been expanding since that time. So we actually want to see the first visible light, but you need an infrared telescope today to see it. And that presents a whole host of really tough engineering challenges. But we're not so much replacing Hubble as we're complementing it. Mm-hmm. We're kind of building and standing on the shoulder. We're building on Hubble and standing on the shoulders of Hubble.
Yeah. And I mean, having that sensitive infrared instrument, I mean, we've talked a bit about how this is going to take us right to the edge of the observable universe, but we're going to be able to see a lot of other targets, right?
Oh, yeah, absolutely. I mean, a lot of the science requirements that drive our design are seeing those very first luminous objects, but with an infrared telescope, it's a great general purpose observatory. I mean, it's going to be great for looking at new stars and new planets forming in our own galaxy, exploring the atmospheres of nearby exoplanets. Those phenomena are great if you have an infrared telescope, because they happen at temperatures at which the light is brightest in the infrared. I mean, infrared light is basically, we don't see it. It's a little bit redder than visible light, but we feel it as heat. And, planets form at temperatures that are cooler than their parent stars, so they're brightest in the infrared. So if you have an infrared telescope, that's the best tool to use to see them. Infrared light doesn't get scattered like visible light does, shorter wavelengths of visible light do. So you can look through these dusty stellar nurseries where a lot of planetary systems are forming. We've seen pictures like that of Hubble from, say, the Orion and Eagle nebulas. You see little protoplanetary disks forming, but you can't see inside the disk to see the planets actually forming. Well, with infrared light, you can probe and you can look right through the dust and see into these stellar nurseries and see stars and planets being formed. And with spectroscopy, we can actually identify the chemistry of atmospheres of planets around nearby exoplanets. So if we detect free oxygen, ozone, water, methane in the atmosphere of a rocky exoplanet, a few tens of parsecs away, I mean, that's a game changer, right? Because that says, wow, maybe life could exist there on this rocky planet around a habitable zone of a nearby star, and it's got all the signposts we associate with life. I mean, it's pretty exciting stuff.
Yeah, and so, I mean, we're right at the edge of really getting a sense of whether or not there are, how these the extrasolar planets sort of operate, getting a lot more information about this. And one of the really kind of tantalizing ideas is that we're going to be able to start analyzing the atmospheres of these extrasolar planets, either directly the way Spitzer has done, right, but possibly as well using like some kind of star shade. So, with the sort of real goal is really getting an understanding of not only are these planets there and are they of the size and mass of the Earth, but are they actually, what kind of atmosphere and stuff do they have? So can you talk a bit about sort of how James Webb is going to help us to analyze the atmospheres of these other worlds?
Sure. So we basically use spectroscopy, which, is kind of like passing light through a prism that splits it into the colors of the rainbow, its constituent colors. Well, with spectroscopy, that's what you're doing. You're taking light from an object and you're spreading it out into the colors that make it up. And every element of the periodic table and every molecule has a unique spectral fingerprint, so to speak. So it's almost like a spectrograph looks like a stock plot. If you plot, amplitude versus wavelength, and does this, and each of those lines at a certain wavelength, you can look, for example, if you heat up hydrogen or you heat up methane, or you pass light through it, it'll absorb or emit light at very specific wavelengths. And so you can go, oh, I see methane, I see O2, I see O3, I see water. So with spectroscopy, we can sniff the atmosphere of a exoplanet and actually see the chemical makeup of it. It's just like you would do in a lab in high school when you're doing spectroscopy, but here you're actually using a very sensitive instrument on an exquisitely sensitive telescope to get a spectrograph of atmosphere of another planet. And That's how we do it, spectroscopy. So it's maybe not the sexy picture. It shows up on the above the fold in the front page of the New York Times. Looks more like a stock plot, but there's a lot of science in those things that look like stock plots, those spectrographs.
Well, I think one of the things that is sort of the, we hear these announcements of like, oh, there's this planet, this Earth-like planet discovered around this other star. But the problem is that it's, we think it's in the habitable zone, but here in our solar system, both Mars and Venus are in the habitable zone. It's only when you actually study their atmosphere that you really get a sense of this world as a place that you'd want to spend any time on, right?
Yeah. You sniff Venus and you detect a lot of sulfuric acid and carbon dioxide, and it's warm, and you're like really warm, and you're like, well, it doesn't sound too much fun. And then Mars, there's not any free oxygen there. It's kind of thin and cold. So exactly.
Now, can we talk a bit about just like the place you're going to be putting the telescope and sort of how you're going to be launching it? So can you talk about like how that's going to play out, where you're going to launch it, on what, and to where?
Sure. So we're launching it from, we're going to L2, Lagrange point number 2. So in any two-body problem, gravitationally, there's 5 kind of stable or metastable places where the gravitational attraction of those two bodies kind of works together. And so we're going to a place about 1.5 million kilometers in the midnight sky. So about a 1.5 million kilometers or 1 million miles away from the Earth, opposite the sun. And we're going to orbit the sun, but we're going to kind of follow the Earth as we orbit. And be 1 million miles away in the midnight sky, if that makes sense. And we're getting there on an Ariane rocket. The James Webb Project's an international project. Canadian Space Agency and European Space Agency are NASA's partners. And one of the things that the Europeans are providing, besides 2 out of the 4 cameras and spectrometers, is a rocket. So we actually launch on an Ariane 5. I've got a model one here. It's a really nice rocket. Just had its 74th. This is a 100th scale model. So the real thing stands on the order of 180 feet tall ish. It just had a 74th successful launch this week, and it's a really nice launch vehicle. It's built in France, and it's launched out of a spaceport in South America. In French Guiana, which is about 5 degrees above the equator, not too far from the mouth of the Amazon. If anybody ever saw the movie Papillon with Steve McQueen, and that penal colony he was on, Devil's Island, that's really close to that launch site. So that's where we're launching from, and we're in a direct flight. We don't orbit first. We just leave the Earth and go right to L2. And it'll take about a month to get into orbit around L2. And so that's where we're going to hang out. And the reason we're going there is the Goldilocks place. Infrared telescope, infrared light heat radiation. If you want an infrared telescope to be really sensitive, it needs to be really cold, so it's not looking at its own heat, if that makes sense. And that's why Webb looks like this. So here's a little 80th scale model, which is almost the same scale as this thing. And you can see this doesn't fit in this, doesn't fit into that. So so we have to build it so you can fold it up very compactly, like origami, to fit in the nose cone of the rocket. And then when it gets into space, it unfolds over a 3-week period to look like this. And notice it doesn't look like Hubble. It's the feature. You've got this nice diamond-shaped 5-layer umbrella, size of a tennis court, and you have this beautiful literally gold-plated mirror. And the mirror is not one piece; it's actually 18 segments. Each segment is a hexagon about 5 feet in diameter, and 18 of them tile together to make one nice big mirror. And this thing's stowed. The outer mirrors fold back like the leaves of a drop leaf table, and that helps. And the tripod holding a secondary mirror folds up, and the sun shield Z folds and all folds up. And this whole thing folds up very compactly to fit in the rocket. And so when it's out at L2, it will look like this. And from that nice vantage point in space, that's where it can do some nice infrared observations, because it's away from the big room temperature object that is the Earth. It would never get cold without it. So what happens is we always keep the sun on this side of the observatory, and this side's always in the shade. And just by being in the shade, this side will get down to temperatures on the order of 40 Kelvin, which is almost 400 degrees below 0 Fahrenheit. So air is not only that air is a solid at those temperatures, and that makes for a really tough engineering problem because things shrink when they get cold, but we're building this at room temperature in a 1G environment in air, but it's got to work at 40 Kelvin in 0G in a vacuum, and so we basically have to build it exactly wrong at room temperature,
right?
So that it's exactly right at its super cold operating temperature. So that makes for a really crazy design challenge. We got to build it. It's so huge it won't fit in a rocket, so we got to fold it up. Build it to be folded up and deploy in space, and then we had to build it exactly wrong, so it'll be exactly right dimensionally because it's so cold when it's operating. And then it's so big, and the boundary conditions of the hot side and the cold side are so hard to. You can't practically duplicate that in the test chamber on the ground. So testing is a real challenge. We basically have to test the big pieces that make it up separately, and then analytically show that when we put it all together, it's going to work.
And you only get one crack at this, right? I mean, it's not going to be in a serviceable location the way that Hubble was. L2's pretty far away, and you're not going to be able to go there.
That's correct. We don't have any capability today to service it, and none's definitively planned in the near term. So we're building it so it's going to work the first time. But that's not unusual when it comes to spacecraft. It's Space Station and Hubble that are the oddballs that were designed to be serviceable and routinely maintained by people or robots. The communications and weather satellites we depend on daily and take for granted are built to be launched and work. So we have a lot of margin built into the design. We have a lot of redundancy built into the systems. So that's not to make light of the risk of this thing, because we're really pushing the envelope engineering-wise in a lot of ways on this machine. But we are building it with practices that are tested and true over the last several decades of how to build a satellite and know it's going to work when it's in space.
Here on the show, we often joke about how people don't put enough reaction wheels on their missions. That seems to be the thing that kills them. So can you give our audience comfort that you have put enough reaction wheels onto this mission?
Well, we've got 6, and we need 3 for ordinary pointing and schemes. So we've got double redundancy there. Our wheels have a lot of heritage to the wheels that are on the Chandra X-ray Observatory.
How are they doing?
Well.
Good. Okay.
I'm not sure exactly
how many are left.
How they're doing.
Yeah.
But I think we're good. But yeah, there are some moving parts on this thing. The reaction wheels are the biggest moving parts, and we need those to point. Each camera has little filter wheels in it, little things that rotate, and we have what else do we have? Now, those are mainly the moving parts, the things that are going to ultimately limit, and moving parts where. So, but hey, we've had spacecraft up there forever that are way beyond their lifetime. I mean, I remember the International Ultraviolet Explorer IUE that lasted more than 20 years, and I think they finally turned it off because multiple senior reviews were like, okay, let's move on. Which one is it? Spirit or Opportunity still running, and it had a 90-day design life. And it's how many years later? Yeah. And then, but ultimately, what may limit the life of Webb is fuel. So unlike Hubble, it needs fuel for orbit maintenance and for momentum management.
Right, because L2 is unstable, right? It's not a stable Lagrange point.
Right. Unlike L3, 4, and 5, L1 and L2 are metastable. They look like saddles if you imagine the gravity potential that's at those points. So it's kind of stable in one direction, but unstable in the other. So you need a little bit of fuel to maintain your orbit. We also need fuel to momentum dump, which is, hey, we point with the momentum wheels, but eventually you got to rebalance the speed of your momentum wheels. And when you do that, you need to react against something. Hubble has big torque bars on the side, big electromagnetic torque bars on the side of its body, and it's in low Earth orbit, like 300 some odd nautical miles up. Well, it can push against it can react against the magnetic field of the Earth in low Earth orbit, and so it doesn't need fuel to rebalance its momentum wheels, respin them. We need to react against something, and that reaction is little tiny rocket thrust. So ultimately, fuel will probably limit the life of this thing.
How long do you think that you'll have fuel for?
Well, we're putting enough fuel on board to last at least 11 years after launch. So that's 10 and a half years of science ops. We got a nominal 6-month commissioning period where we have to deploy, we have to let everything cool down at the right rates in a controlled fashion, turn everything on, get the mirrors lined up, get the instruments all tuned up, and start real science operations about 6 months after launch. So we have enough fuel with 3 sigma dispersions on the launch vehicle and conservative assumptions about us not scheduling observations very well to last 10 and a half after commissioning's over. But which means if we do a good job and we get a normal launch like we should from the Ariane, we could last much longer than that. We certainly hope to.
Yeah. So sort of running out of time now. So let's just give people a way to kind of get excited about it. Let's have what are some big milestones coming up, and when will we see the launch?
Okay, so the next big milestone is we're going to take the telescope and instrument package. So the whole cold half of the observatory right here, it's built. We're going to shake the bejesus out of it in just a couple of weeks. We're going to stick it on a really big vibration table and also stick it in a big, giant acoustics chamber and shake it really hard and yell at it. And that's to simulate the mechanical violence of the launch environment. And it's also a workmanship check. So that's a huge test. That's coming up. That's the next big thing. When we're done with that and we do some testing afterwards to make sure that everything's okay, early next calendar year, we send it to Texas. It goes to Johnson Space Center for end-to-end optical testing of this whole deployed system. We took a relic of the Apollo era that's a giant vacuum chamber. It's 8 stories tall from the Apollo era, a relic of the Apollo era, and we upgraded it, turned it into the world's nicest, super clean cryo optical test facility, and we're going to test it in that. In the meantime, the spacecraft bus itself should be being built at Northrop in Redondo Beach, California. It should be done in a number of weeks. The sun shield will get put together in the next couple of months, and then those 2 elements come together and get built. And then, so this part and then this part will meet in early 2018. They'll get put together. We'll do some final testing, actually do another shake, but of the whole thing. And then in the summer of 18, we stick it on a barge. Well, it's not really a barge, it's a really nice ship. And ship it to South America. And then we launch in nominally of October of 2018.
Oh, that's fantastic. So where can people find out more information about James Webb if they want to stay on top of it?
Oh, well, you can go to our website. It's jwst.nasa.gov, or just Google or search on James Webb Space Telescope. Also, we have a Facebook page and a Twitter. So it's at Webb Telescope for Facebook, and it's NASA Webb for Twitter. And we're in the news a lot. So check us out on our website or Facebook or Twitter.
Sounds great. Well, thank you very much for joining us today, Paul, and good luck with all of the the shaking and assembling until October of 2018. We're all really excited about what this telescope is going to give us. So thanks for joining us.
Thank you. My pleasure.
All right. So let's see. I've got to fix some things here. And bring the rest of the guests in. All right, so let's move on to, I guess, the next person who's going to talk, Kimberly. Why don't we talk a bit about MAVEN's 1-year anniversary?
Yeah, so MAVEN, which is the Mars Atmosphere and Volatile Evolution, MAVEN, is celebrating its 1 Mars year anniversary. So that is about equivalent to 2 Earth years. It entered Mars orbit in September of 2014, and it has done 1 Mars year of science observation, which is its mission lifetime. And in that 1 year, it has revolutionized our understanding of the Martian atmosphere and its evolutionary history. Things like understanding the current and past atmospheric gas loss on Mars, which is essential towards understanding how the planet has evolved in terms of habitability, how the sun's solar cycle comes into play in interacting with the Martian atmosphere, the fact that Mars is surrounded by an interplanetary cloud of dust, which also interacts with the atmosphere to make a layer of metal ions, the diffuse aurora that Mars has, getting a full picture of Mars in the ultraviolet, which personally I think that's one of the most cool pictures of Mars that I have ever seen, is looking at Mars in the ultraviolet. All of these things, these wonderful discoveries, really helped us understand Mars's atmosphere. Luckily, MAVEN is in prime condition and it's in prime health. All the systems and instruments are still going at full strength, and it has been approved for another Martian year of science observation through 2018. So I think that we can look forward to even more wonderful discoveries from MAVEN and trying to understand our nearest neighbor. So it would be a pretty great upcoming year, I think.
I got nothing to say on that. Go MAVEN.
It's awesome.
More
MAVEN.
pictures, more better.
Keep going.
Yeah.
I want some more awesome Mars pictures in the ultraviolet. It's great.
All right, I'm going to move on. Sorry, we're going to go pretty quick. We got not a lot of time left. Sandy, let's talk about the Sputnik Anniversary. Oh, you're muted, Sandy. Still muted. Oh, there it is.
It's been 59 years since Sputnik launched, which is sort of exciting. I think everyone knows Sputnik launched in October 4th, 1957. It was the first human-made spacecraft in space to orbit the Earth. It was launched by the Soviet Union, and it freaked out a lot of people in the U.S. If you've seen the movie October Sky, it's about Homer Hickam and his friends building rockets out in coal mining town, outside of a coal mining town. So Sputnik was about the size of a beach ball. It wasn't very large, and it was spherical because it had these vacuum chambers in it, and having a sphere made it easy to have them pressurized. And it took about 100 minutes to orbit the Earth, and it really just sort of changed our lives as we know it. It set off the space race. It led to the Earth. It led to the U.S. Launching humans to the moon eventually, the Soviet Union putting the first humans in space, the first man in space, and the first woman in space, and the U.S. playing catch-up until the U.S. finally landed people on the moon and effectively won the space race. So it was it's amazing what a little, was 100, not even 200-pound little spherical ball that had a little radio signal coming off of it. It's amazing what it could do to sort of change the world as we know it. It really did instill a lot of fear in the U.S. because having something in orbit, all of a sudden people felt like they were being spied on. We have spy cameras in orbit now and all sorts of other things we just don't know about. And Sputnik also caused the formation of NASA. It started out as NACA, the National Advisory for Aeronautics, and eventually became NASA. So pretty much everything that we care about, everything that we talk about here on the Weekly Space Hangout stems pretty much from Sputnik.
Well, I guess next year is when people are really going to have a big party about it because it'll be the 60th anniversary.
Get excited.
Yeah, 59th. I don't know. What's the 60th anniversary? Is that some kind of... Should we get it some kind of present? I'm sure you're Googling it right now. Is it... Yeah, is it platinum? Is it...
Well, I think 50 is diamond.
Yeah. Whoa, 60... Here,
60th is diamond. 60th is diamond.
Is diamond. Okay, great. So we should all buy Sputnik a diamond to say thank you for existing.
Here the theme is charity, so donate to your favorite space nonprofit.
Right. All right, Paul Metzetter.
Yes, that's me.
Let's talk
what do you want me to talk about?
Ultra cool. Was it ultra cool,
ultra cool,
ultra strange brown dwarfs?
Brown dwarfs, yeah. So brown dwarfs are neither brown nor dwarfs. They're somewhere in between planets and stars. We know that if you accumulate enough mass, eventually the pressures and temperatures in the core reach a certain critical threshold. Nuclear fusion takes over, and you have a star. But you can have big blobs of gas and dust that don't quite reach that threshold. So they're bigger than a planet and they're not orbiting another star, but they're too small to be called stars on their own. And there's this class of objects that we call brown dwarfs. And we don't really know a lot about brown dwarfs because they're very dim and they kind of tend to hang out by themselves. They're not paired up with other stars or other objects. They just float around on their own. So they're difficult to find, difficult to study, poorly understood. And some astronomers did a survey looking for some more brown dwarfs to try to get a handle on them. And it turns out they're a little bit weirder than we even thought they could be. Some of these brown dwarfs that they found in their survey are either too cold or too hot. They look too red. They look too blue. The main point is there's not just one kind of thing called a brown dwarf. It turns out brown dwarfs have all sorts of different varieties, and we just plain don't understand them.
And of course, having the James Webb Space Telescope will be like the perfect device for studying and analyzing more of these things, right?
Yeah, exactly. Because they're so cool, especially the ultra cool ones, they emit a lot in the infrared band. So if you have a nice infrared telescope, you can pick them out much better.
Now, how cool are we talking about here?
Like 3,500 Kelvin, which is still like super hot.
Yeah.
But when it comes to stars or wannabe stars, it's pretty cold.
But I recall doing an episode and, that these brown dwarfs can get pretty cool. I mean, how far down do we think these things can go?
That we just don't know. Because the cooler they are, the less light they emit, so that even harder it becomes to detect them. And that's why we need things like the James Webb Space Telescope or ground-based infrared surveys to try to pick out more of these objects. Missions that look for wandering or rogue exoplanets are also going to pick up a lot of these brown dwarfs.
All right, I've got a picture here. I guess it's the you shared a story here, and I guess it's the green one at the very middle.
Yep, there it is. It's not. I don't think it's green in real life.
Right, they were just picking colored, it out.
Yes, yeah, it's that one.
Yeah. Okay. All right. Yeah, I know you actually can't see, so I appreciate you playing along, pretending like you can. Nice work. You are a total professional, Paul Metzetter. Okay, well let's move on. Apologize for going so quickly, but as we got a lot of stories, a lot of people, and a guest that I just could have spent all day hanging out with. So, Kimberly, let's talk about giant plasma balls ejected from a star.
Giant plasma balls detected. Yep, that's right.
Ejected.
Ejected from.
Detected. Ejected.
Yes. Exactly. I'm not going to try and say that 5 times fast.
There was an ejection detection, is what I'm saying.
Sure.
Okay.
I'll leave that one to you.
All right. Anyway,
there is another mysterious star. Does not have any alien megastructures or anything like that. But astronomers have been looking at this star, V Hydrae, which is a red giant, about 1,200 light years away from us. And they've been studying this for over a decade and have noticed periodic, really large plasma flares coming from the direction of this star. And it's really mysterious because red giants should not be able to make such large, very hot plasma flares on their own. They're at the end of their lifetime. They have little to no nuclear power left in their cores. They just don't have the energy available to make these kinds of plasma flares that we've been seeing. And they come at very regular 8.5-year intervals. So after observations with the Hubble Space Telescope and the submillimeter array in Hawaii, they've detected not only just one or two of these, but actually a whole stream of these plasma flares, these plasma balls, essentially coming off of V Hydrae, and have come to the conclusion that it's probably because there is an unseen companion star in orbit around this red giant. It's not unheard of at all for a red giant to have an unseen companion star that fluctuates the atmosphere and such. So what they think is that this star is on a very tight, very elliptical orbit, such that on its closest path, it actually passes through the outer atmosphere of this red giant. And when it does that, it starts to pick up and grab some of the material from the red giant star and fling it about in an accretion disk, which then flings out these plasma balls into space. These are going at an appreciable fraction of the speed of light. And so over the 11 years that they've been observing this stream of plasma balls, they essentially can backtrack the trajectory of them. And they think this has been going on for over 400 years.
Wow, so it's almost like a slingshot that the star is coming in, passing through the red giant, blasting out these plasma balls, and then as it heads back out on this regular basis.
The rest of the gas dissipates. But I think what's really cool is that they actually not only think that this unseen companion star is causing these plasma balls, but they think that this kind of mechanism might also be responsible for creating the various wild shapes that we see in planetary nebula. So planetary nebula, the dying gasp of these red giant stars as they expel their outer atmospheres, we see them in all shapes and sizes and colors with streams of different types of gas and sometimes crazy dumbbell-like shapes. And we have no idea really what makes one planetary nebula look one way versus another. And so perhaps this mechanism with an unseen companion star interacting with the outer atmosphere of this red giant might actually be shaping the future planetary nebula.
That is super interesting. Now, if this star, this companion star, is actually passing through, it almost appears like it's passing right through the outer atmosphere of this red giant. Mm-hmm. Is that going to, is it experiencing any drag as it passes through? Is this going to cause it to spiral inward at all? Is there sort of
eventually, yes, because it is interacting with the outer atmosphere, and the red giant is losing mass as well as it expands. So yeah, the orbit will decay. It'll probably still take many hundreds of years for it to do that, and in the meantime, it still gets to interact with the outer atmosphere.
That's really interesting as a way to explain potentially the different shapes of planetary nebulae. I really like that a lot.
It'd be very cool if that were the case. Unfortunately, you probably won't actually ever directly detect this companion star just because red giants are so frickin' bright. You're never going to be able to see such a close companion star. But perhaps if this sort of mechanism keeps going and we can observe it again in another couple of years, that would be a pretty good indication that we're on the right track.
Perhaps some new...
Perhaps a new telescope.
A new telescope, something in the infrared spectrum might help us out. Something that's really ideally suited for, looking at objects bright in the infrared. So
if only there was such a telescope launching in a couple of years.
We can only dream. Cool. All right, Sandy, let's talk about Hurricane Matthew and its close call against the Space Coast.
Let's talk about Hurricane Matthew. So if you've been following the news at all for the last couple of days, there's been this giant hurricane that has been coming up through the Caribbean. It completely has devastated Haiti. It's done damage in Cuba. It's done damage in the Bahamas. And it just rolled up the coast of Florida. And so if you've been to Kennedy Space Center, like Fraser and I were about a month ago, you've noticed that it's very low lying, that a lot of it is just a couple of feet above the level of the ocean level there. And so with these storm surges that were predicted, people were worried that this hurricane, if it made landfall, was going to completely take out U.S. space infrastructure at Cape Canaveral, at Cape Kennedy. Luckily, all it did was, there's been a little bit of roof damage, there's been a little bit of water damage, but fortunately everything is okay. But will things be okay during the next hurricane? Will we have to start launching more things out of Wallops. Will we have to start launching things out of Vandenberg? It's sort of hard to launch things onto equatorial orbits out of Vandenberg. Will we have to have the Russians launch things? The reason we launch things out of Kennedy Space Center is because it's closer to the equator than other points in the US, so you don't have to use a lot of fuel to get into an equatorial orbit. So we got lucky this time, but next time we may not get so lucky.
So you think that, I mean, is this sort of one of the big implications of global warming, or global weirding, is that we're getting these strange events, more common hurricanes?
Won't necessarily be more common, but the large, intense, really destructive ones they'll be more intense and destructive. There won't necessarily be more hurricanes, but the ones that do show up will be worse. And as sea level rises too, that's going to put Cape Canaveral at risk as well. So in short, we're screwed. Sorry.
Well, I mean, it's not just that, right? We're also facing the problems with water levels rising, right? So I got a view here. So I'm just showing a video of Hurricane Matthew and sort of its path. It came up. I know it went through Haiti and went through Cuba and then made its way up and just cross up into the onto the side of Florida. So, now we've moved on to something else from NASA, which you can't see. So, I mean, are there any solutions? You say, like, let's move to, let's put more launches out of Vandenberg.
You can do more launches out of Vandenberg. They're going to launch InSight out of Vandenberg eventually, I think. But if you want to launch onto more equatorial orbits, you really want to launch from somewhere closer to the equator. And so having a launch facility on US soil is useful. And so now we're showing with SpaceX and Blue Origin that you can land pretty much anywhere, but launching requires a ton of infrastructure. And so all of that infrastructure, the vehicle assembly building, all of that is at Kennedy Space Center already. So where would you relocate that to?
Yeah. Guam?
Puerto Rico, maybe?
Puerto Rico, yeah.
I don't think Arecibo got hit. They certainly got rain and a lot of wind. And
yeah.
All my former coworkers' dogs were not enjoying the tropical storm that washed over. Puerto Rico's been having droughts and electricity problems and water rationing, and one of their substations blew up a couple weeks ago, so like a quarter of the island didn't have electricity.
There's a question in the chat. Lost Lucidity asks, how vulnerable to the Space Coast are contingency plans in place? It's not like hurricanes are a new threat. So, I mean, they are prepared for hurricanes. We've seen this happen time and time again in the past. So, what do they do as hurricanes are coming into the coast?
I think, there was mention at the visitor center that they had a number of staff hunkered down with the Atlantis space shuttle, and that I think they probably just lock everything up, tie down anything that moves, and clear everyone out, because people's lives are more important at some point than infrastructure. A number of my friends who work at Kennedy, they evacuated to Kissimmee and Orlando.
Okay, so I am going to try and show this next thing as video. Paul Metz-Sutter, let's talk about the successful test of the new Shepard.
Yeah, so say you are an aspiring space tourist and you'd like to take a suborbital flight on one of Blue Origin's new Shepard rockets. Your first question might be, what would happen if the rocket were to, blow up? What would happen to me? Well, Jeff Bezos has an answer for you. He says you'll be A-okay. He has tested a crew escape device on the rocket, where if the rocket is in the process of launching and going into space and something is about to happen, the crew capsule can detach and parachute safely back to the Earth. And they performed a successful test of this concept this week, where the rocket itself, or the crew capsule, detached, returned to Earth, and then the rocket itself went on up into space. They didn't blow it up on purpose. That was not a part of the test. It went up into space and then landed safely back on the Earth. So this is in contrast to the what Elon Musk and SpaceX is doing. Right now, Jeff Bezos is focusing on suborbital flights, so just going up to the edge of space and then coming back down, solely for the purposes of tourism, of being able to say you've gone into space and paying a lot of money for that privilege, that money will go to fund more ambitious endeavors.
One of the things I thought that was pretty funny was just that in sort of leading up to this launch, they were pretty clear that this was probably going to be a disaster. That they, or I mean, not a like people were going to die, but that it was going to fail. That this was
not going to work.
It was not going to work. This was not going to work properly, and yet it actually did, which is sort of a strange reversal. Usually, SpaceX says this thing is going to work, and then it turns out that it, with the first few of those tests when they're testing brand new advanced technology, and they were really pushing the envelope of what was possible, they would run these tests and they were hoping it was going to work, but it didn't work. It was very strange to me when Blue Origin said, this is probably not going to work. I mean, this is the first time we've tested it. And then the thing just worked.
Maybe behind the scenes, they knew like 100% sure that it was going to work, but they're going to be all cool about it, just to rub it in Elon Musk's face.
Oh, that's so mean. Yeah. So that's great. So now will you get on board one of the first launches of this thing?
I would love to. I don't think my wife will let me.
No, not until other people have gone before us.
Not until I sign that life insurance document.
Yeah, absolutely. All right. So, and then you've got one other piece of news, Paul, which is that it's Observe the Moon Night coming up on Saturday.
I said that?
Did you? Somebody? Oh no! Wait, maybe that was Dave Dickinson who was thinking he was going to join us. It's under your name. So
I see.
So
okay,
It's the International Observe the Moon Night.
Yeah.
Go observe the moon.
We've got an article on Universe Today about observing the moon. That would be best if you spent that time observing the moon.
My office mate is the outreach coordinator for here. And so last year she couldn't find her moon before International Observe the Moon Night. And she was so sad. It was really a travesty.
Couldn't find her moon. Like she what?
Into a meme. It was amazing.
I can't find the moon or my moon.
Yeah, like my moon is missing and it's International Observe the Moon Night.
Awesome. All right, cool. So now we're sort of reaching the end of the show. I'd love to give people a chance to where we can find out more. So Kimberly Cartier, where do people find out more about you?
People can always find out more about me by following me on Twitter at AstroKimCartier or going to my website, which I will soon be revamping, which is KimberlyCartier.org. And if you happen to be in the central Pennsylvania area on October 15th, you should totally stop by the Penn State Department of Astronomy and Astrophysics for our Astro Night, October 15th. More information is at astro.psu.edu. Definitely come by.
Fantastic. Oh, turns out that was Susie Murph put in, one of our producers put in that we should be observing the moon. So now I understand.
Thanks, Susie.
ObserveTheMoonNight.org. Oh, someone put it into the chat, which is perfect. Paul Matt-Sutter, where do we find out more?
You can find out more on my website, pmsutter.com, and also by following me on Twitter and Facebook at Paul Matt Sutter. And you can also listen to another podcast I do called Ask a Spaceman, askaspaceman.com. And if you've got some extra money and you don't want to take suborbital flights with Blue Origins, you can send them to my Patreon at patreon.com/pmsutter. I won't blow you up either.
How is the dance going?
So the dance thing, Song of the Stars, is going really well. The films are nearing finishing production. We had to commission an original score so that we owned all the licenses and all that. That is almost done. The finishing touches are going on the traditional film and the planetarium film. I just saw some test footage a couple weeks ago. It's looking really great. It's going through one more round of polishing and cleaning up. So it's almost there. I've been saying that for like 6 months, but
but I mean, you are the busiest person I know, apart from me, maybe.
Apart from you.
Yeah, which is that you've got like so many projects on the go all the time, and podcast, dance, show, teaching, researching,
and showing up on the Weekly Space Hangout.
Showing up on the Weekly Space Hangout, which is probably the most important job that you have. So,
yeah, well, it's number one on my calendar.
Oh, that's fantastic. Wonderful. All right, Sonny Springman, where do we find out more?
I am on Twitter as Sondy, Sondy, and I just put a new homepage on my website, sondy.com.
You're just Sondy in all the places. You've been doing
Except
this internet
some
thing.
punk on Instagram has Sondy, so I'm Radar Sondy on Instagram.
I wonder if there's some way.
I have friends who worked at Facebook. I'm sure I could.
Just wait till they stop using their account for a while, and then you can take control of it. So that sounds good.
That's how I got the Sondy username on Twitter. Someone hadn't tweeted in 4 years.
Yeah, and you said it's me, by the way. I should have it.
I asked someone at Twitter, and I got it.
Oh, that's great.
Yes.
Wonderful. And I think, Paul, you stuck around. So since you are still here, why don't we'll give you an opportunity to say to let people know once again where they can find out more about you and your fabulous telescope.
Yes, just do a web search on James Webb Space Telescope. Visit our webpage, jwst.nasa.gov, or check us out on Facebook or Twitter.
Fantastic, and do let us know how that launch works out.
Oh, sure will.
Fantastic. All right, so once again, I'm Fraser Cain, publisher of Universe Today. If you haven't already, subscribe to this show. That would be great. Also, I hope you noticed I've been trying to up my production game this week and did a bunch of stuff. So putting more videos and pictures and stuff. So I saw people mention that my microphone went a little blurpy for a second there. Thanks for catching that. As always, if I do anything wrong, anything that bothers you, please let me know. FraserCain@gmail.com. Just send me an email and go, your production problems are the following, and then I will try to improve for next week. Once again, thanks for watching. Thanks to our panelists and special guests for joining us. Thanks to the fans who are watching this live, and thanks to the good folks from the WSH crew who really act like the production of this whole show. We really appreciate their help. And if you want to find out more, go to wsh-crew.net and you can join this wonderful community. All right. Thanks, everyone. We'll see you all next week.
See ya.
I can do this one last thing of everybody. Boom. There's everybody. Say goodbye.
Bye.
There we go. All right. Thanks.
Thanks, Fraser.
Stop streaming.
I get to go make slides for a public talk tonight, and I just want to go sleep.